Hello, this is your conductor speaking. This is a Unit 5 bound V train. This station is Unit 5.1, Intro to Systems of Equations. Transfer is available to the Mr. Bolel's Flipped Classroom YouTube channel by mousing over to the profile icon and hitting click. The next station is Unit 5.2, Solving Systems by Graphing. Stand clear of the closing doors, please. Hi friends, how you doing? So, welcome to Unit 5. Back in Unit 4, we focused primarily on one line at a time. However, we closed it out by discussing two special pairs of lines in the form of parallel and perpendicular ones. Those special relationships between them are useful in the context of finding equations, but thinking more broadly, any two linear equations, not just parallel and perpendicular ones, can be considered in pairs, which leads us to the guiding idea of Unit 5, these things that we call systems. Now, what do you think of when you hear the word system? There's a reason mathematicians picked this word. Pause the video, take 30 seconds. What do you think of? What comes to mind for you when you hear the word system? Come up with something. Go. Alrighty, well, maybe I've psychologied you into making this decision, but maybe you came up with something different, I don't know. For me, the first thing that I think of when I come up with, or when I hear the word system, is a subway system. Maybe if you are a little bit more scientifically inclined, then you could think of something like the nervous system, right? Or really any of the systems that make our bodies work. If I'm thinking of a subway system, what is it really? Well, it's a bunch of individual trains, but I can transfer between them at different stations, right? So they're connected in some way. The same thing with a nervous system. It's a bunch of individual nerves, but they all come together at different nodes that allows different electrical signals to travel through them. So the idea is that a subway system, right, or a system of subways is a bunch of connected subways. They're joined together somehow. Same thing if I'm dealing with a nervous system, right? It's a bunch of connected nerves, and so on and so forth, right? For any of the examples that you might have come up with. So by extension of that logic, what that means for us is if I'm dealing with a system of equations, right? A system of subways is a bunch of connected subways. A system of nerves is a bunch of connected nerves. So a system of equations, logically, should be a set of connected equations. Our goal for today is to figure out, well, how are they connected to each other? To motivate this idea, let's try an example. So, let's take a gander at this guy. As you're packing up to leave for school, you're suddenly struck by a terrifying realization. Last night, you completely forgot to charge your devices. In a panic, you check their power levels only to find your laptop sitting pretty at 13%, while your phone is barely hanging on at 2%. From past experience, you know that your laptop regains about 2% of its charge every minute when plugged in, while your phone will gain 3% per minute. How many minutes will it take for your phone and your laptop to charge to the same percent? And what will that percentage be? So, just like as in units past, our goal is to algebraic representation, model this scenario. So, take 30 seconds, take a minute, pause the video. The hint that I'm going to give you is that perhaps one equation, if that discussion that we had before has any bearing on this, perhaps one equation isn't going to do the trick. What are the variables that we're keeping track of here, right? And if this idea of needing more than one equation is going to guide my hand in any way, how might I use that to accurately represent what I'm told? Alrighty, take 30 seconds, pause the video, see what you come up with. Have fun. And stop. Okay. So hopefully you've noticed here, right? I've put this idea in your mind that one equation might not do the trick. Well, the idea is that I have not just one, but two things here that I need to keep track of, right? Both a laptop and a phone are gaining charge simultaneously. The laptop, well, if I'm thinking about how I'm going to calculate its charge, well, I know that it's starting at 13% and it gains about 2% every minute. Same thing with the phone, right? It's going to start instead at 2%, and then it gains 3% per minute. You've also hopefully noticed that if we're dealing with these two things, we might need two variables. I'm not just keeping track of one quantity. I need to deal with both the amount of minutes that I charge for and the percent that I charge to. So this idea of needing more than one equation, more than one variable, is coming back to bite us in the butt. So, like any word problem, I want to start by defining my variables. So I'm going to pick m, maybe, to represent the first thing I want to keep track of, which is the number of minutes that I'm charging my devices for. But the other thing that I'm interested in, right, is the percent that they charge to. Thinking strategically, maybe I'll pick p as my variable to represent the percent of the charge that my laptop or phone is at. And again, I've got two things that I need to keep track of, right? I need something to tell me what the laptop is doing, but I also need something to tell me what that phone is up to. Now, if I'm thinking about how to model these things, I'm interested in finding the percent that my laptop or my phone is at. So that's my P, right? My percent charge. Well, how would I calculate the amount of percent charged for the laptop? Well, I know that the laptop starts at 13%, but then it also gains 2% per minute. Thinking back to some units past, well, if I multiply 2% per minute by the amount of minutes that I charge, that should give me the amount of percent that I gain. So percent total would be 2m plus 13. Same thing for the phone, right? It also wants to talk about its total percent. And here, its total percent, well, it gains 3% per minute. So multiplying 3% by the number of minutes I charge will give me the amount of charge I gain. And then it's starting at 2. So these are my two equations. And the idea here, hopefully you've noticed, well, I'm calling this a system of equations because they're somehow connected. Their connector tissue are the variables. The thing about these equations is that both of them are defined in terms of P and M. Nice. From this, we can define what we in math call a system of equations, sometimes interchangeably called a linear system. Again, all this really is a set of two or more, right? It doesn't just have to be two, but we've got two or more equations, and the thing that connects them are their variables. So we say that they contain the same variables. So the example that we worked with above, that's a system of equations. Some other examples that you might see. So maybe I've got something like this. By the way, this symbol here, this kind of squiggly bracket, this is going to be the symbol that we use to indicate that our systems are connected. So x plus y equals 7 and 2x minus 3y equals negative 11. The way that I would indicate that I want to think of these as a pair is using this squiggly bracket symbol. But it doesn't just have to be two, so maybe I'll give you one that's wild and crazy. I could have something like this. Let's say negative a plus 2b is equal to 0. b minus 5c is equal to 1. And a plus b plus c is equal to 3. Right here I've got three equations with the same three variables, a, b, and c. So given a system of equations, just like a single equation, my goal is to solve it. Well, if you want to solve a system, right, a set of multiple equations, how do you think that the definition of solving might change? Take 30 seconds, take a risk, take a chance, make a guess. Go ahead. What do you think it means to solve a system of equations? Go. Okay, well, if I'm working with a collection of equations, solving doesn't change. The idea of solving is to make it true. But now I've got multiple things that I need to make true, all at the same time. So to solve a system of equations, what we're trying to do is we are trying to find the value or the values, right, of each of our variables that solves not just one, but every equation in the system. So I am looking for something that makes all equations true. I want to get all of them to be true simultaneously. At later points in the unit, we will figure out methods for solving. But right now, I just want us to be able to identify whether or not something is a solution to a system. So, take for example, this guy. I've got the ordered pair 2, 5, and I want to figure out if it is a solution of the system that I gave you above, x plus y equals 7 and 2x minus 3y equals negative 11. How do you think I would do that? How do you think I would check, hint, hint, wink, wink, nudge, nudge, if 2, 5 is a solution of this system? Take 30 seconds. What do you think the method is? Go. Alrighty, well, if you didn't figure it out, I'm going to give it away. The key to this idea is to check, right? And to check, we substitute. So I know that 2 is my value of x and 5 is my value of y. If I want to check that it makes both of these equations true, well, all I need to do is substitute in. So for my first one, I want to see, well, is 2 plus 5 equal to 7? Well, yeah, right? 2 plus 5 is indeed equal to 7. For the second one, is 2 times 2 minus 3 times 5 equal to negative 11? Well, 2 times 2 is 4. 3 times 5 is 15. 4 minus 15 is equal to negative 11. So we can say confidently, yes, that 2, 5 is indeed a solution. By the way, if you played around with the one above, you could show that the solution to this system would be where P, the percent that we charge to, is 35, and that M, the amount of minutes that it takes, is 11. If you want, feel free to substitute in and verify that this pair of values does indeed make this system of equations true. But for now, let's try it out with these two. I've got these two systems of equations. I want to figure out, does each ordered pair work as a solution? Take 2 minutes, pause the video, see what you get. Go ahead. Alrighty, so for our first one, y equals negative 2x minus 4, y equals x plus 4. If I want to check if negative 2, 0 is a solution, right, all I need to do is substitute. So for my first one, I'm going to take y, which is equal to 0, is equal to negative 2 times x, which is negative 2, minus 4. I want to check, is this a solution? So this is equal to, on the right, negative 2 times negative 2 is 4. 4 minus 4 is indeed equal to 0. So it works for our first one. For our second one, right, I want to see, is 0 equal to x, which is negative 2 plus 4. Here, negative 2 plus 4, well, that's positive 2. Is 0 equal to 2? No. So even though the one on the left is correct, the one on the right is not true. Our goal of solving is to make both true. So no, this is not a solution. It does not solve both of our equations. Same thing for b here, right? I want to check if 4, negative 10 works. So for 3x plus y equals 2, I'm going to take 3 times 4 plus negative 10. I want to see, is this equal to 2? So here, 3 times 4 is 12. 12 plus negative 10, maybe I'll just rewrite that as 12 minus 10. Is 12 minus 10 equal to 2? Yes, it is. And for the bottom one, right, I've got y, which is negative 10. I want to see, is it equal to negative 5 halves times 4? So, negative 10. If I take negative 5 halves and I multiply that by 4, feel free to fact check me here. Negative 5 halves times 4. Well, if I take 4 divided by 2, I get 2. Negative 5 times 2 is negative 10. Negative 10 is equal to negative 10. Here it does make both of our equations true. So yes, this is indeed a solution.